Okay, we're going to go over some problems from the linear correlation and regression homework. We're going to look at the problem number 3 here, where we're looking at police officers and muggings. We want to see if there's a correlation between police officers and muggings here. Okay. All right, well, let's see. Let's take a look here. There seems to be a typo here, and I'm going to say that says use the, if we go through and read this, by the way, let's just start from the beginning here. It says bivariate sample data below for the number of police officers on patrol in a small city. And then you see the number of muggings in the same city. So this is a bivariate data. This is your variable X. This is my independent variable. In theory, we can control that. So when there's 20 officers, there were 8 muggings. 12 officers, 10 muggings. 18 officers, 12 muggings. 15 officers, 9 muggings. 22 officers, 6 muggings. 10 officers, 15, and so on. And this is our independent variable. And our dependent variable, this is the number of muggings in that same city. So we got the bivariate pair of data. And let's verify that there's actually, how many data values? 1, 2, 3, 4, 5, 6, 7, 8 data values. So that's a small sample, ladies and gentlemen. Anything no more than 30 is small. But what I started to get to for this question, it says use the 1% level of significance to test the claim that there is a linear correlation between the number of police officers on patrol and the number of muggings here. So I'm going to change that on you to make sure that this is maybe alpha is 5%. Only because I have that in the notes here of 5%. The degree of freedom, remember, is 2 less than the sample size. So it's going to be 2. Degree of freedom is 6. And there we go. And we're going to verify that the critical values are going to be plus or minus 2.447. Now, remember for your formal hypothesis test, your null hypothesis is the statement that rho is 0 and that there is no linear correlation. The alternate hypothesis, the opposite, is rho is not 0 and that there is a linear correlation. And this is going to be what our claim is always in these questions here. They're going to ask us test the claim that there is a linear correlation. So, okay. So let's verify how we get the critical values. And in the TI calculator, I believe it uses the default. So here's what I want to say here. If the level of significance is 5%, half of that is 2.5% in each one of your tails. So the TI comes along and says, well, and let's see if I can scroll out. We can see maybe everything here. Trying to, would be good if we can maybe, I don't know, does that mean anything? If we could try to get it lower. Oh. Zoom app to window. I don't know if that's the best we can do. Anyway, I thought I could make that lower. Maybe I could bring it lower, maybe? Does that kind of help it? Maybe. Oh, that's a little bit better, maybe. Anyway, okay, we're going to kind of see if this is helpful, and it might not be. Might have to, yeah. Okay. So let's go through the process. Now, you want to get your critical values. You're going to go through, I believe, second distribution. It's not going to be inverse norm, ladies and gentlemen. You're going to go to inverse t. So to get the critical values, inverse t, because this is the student's distribution, right? This is a small sample. Remember, small sample sizes. T distribution, student distribution here, n is 8, so it's certainly no more than 30. All right. area to the left is 2.5%. So remember that you use here for area to the left here 0.025. Okay? So in the TI, inverse T, 0.025. That's 2.5%. Notice it doesn't give us an option of center area, right area, left tail area. It's the default left tail area. So you're going to find the critical value that's to the, you need to know the area that's to the left of that critical value. You also need to know the degree of freedom. And 8 minus 2 is 6. Our degree of freedom, if you remember, was 6. Now we're going to paste this in. And sure enough, we get the critical value of a negative 2.447. And it gives you that left critical value. And you also have the right critical value, same value. There's 2 because it's a two-tailed test. So, ladies and gentlemen, it checks out. So, good, we have our information. Now, remember what we're going to get. We're not going to use these formulas. We're going to use the TI. Right? This is a student's distribution. We're going to get a test statistic, which is a t value now. But we need the sample linear correlation coefficient. We may see if it's close to 0. We may see if it's close to +1, -1. We talked about this in lecture. So let's find our sample linear correlation coefficient. Let's find our test statistic, and let's see if we could draw a conclusion here. But remember, when you go and you gather your data, before you even do anything, you really want to draw a scatter plot. So we're going to have to enter this data here, this bivariate data, into our calculator. All right, so let's see if we can do that here. Right, so what we're going to do, if you guys remember, I think you go to Stat, Edit. Now, L1 is available. We're going to put all our X values there. And L2 is going to have all our Y values. So the first X value is 20. We'll hit 20, enter. 12, enter. 18, enter. 15, enter. 22, enter. 10, enter. 20, enter. And 12, enter. These are all the values in my first list. Now the second list, we're going to have 8, 10, 12, 8, 10, 12, 9, 6, 15, 7, and 18. Okay, so this is our bivariate data. We entered the data that was in these tables here. All right, now if you remember, after we do that, we hit second Y. Scatter plot 1. Yeah, we're on scatter plot 1 here. And I think that's the one we need. And then I believe after that we hit what? Zoom. You scroll down to number 9, zoom stat. And oh, we don't see anything there. We'll try that again. We're on, sorry, clear that out. Stat, edit. We're on that data value. Second Y, I think we have to turn something on here. You know, we have to go turn it on. Stat plots. Got to go plot 1 on. I believe. Let's hit enter there. There we go. It was off. We have to make sure it is on. Put on there. There we go. And it is on the first one, and that's what it's supposed to be. So make sure your plot 1 is on, and it's on that first, scatter plot. That's the scatter plot. So now when you hit the zoom, scroll down to 9, we should have a scatter plot. And sure enough, we do. And so, ladies and gentlemen, take a look at this here. What's supposed to happen is your data should fit along a line. Now, When I see this here, I'm kind of a little leery. It doesn't look like my data is going to fit along a line very well. But maybe it will. All right, let me see if I can scroll in. It doesn't seem to be as workable as my laptop. Somehow with the laptop, I can move that whole thing around and you can see that. It's a scatter plot. And anyway, well, it could be a correlation. Let's go proceed with the process, right? So if you said to me, what do you do now with the process? Well, what you would do in your calculator, you go to stat, you go over to tests. You're going to scroll down to, remember what you have to scroll down to here. Linear regression t-test. Linear regression t-test. It's a small sample. Linear regression. And, you know, you're just saying here, x1 is list. The x variable is the L1 list. The y variable is the L2 list. Frequency needs to be 1. And remember, this is supposed to be a two-tailed test, so that's not equal. Now we're ready to hit calculate. And ladies and gentlemen, let's check this test statistic value, that t value. We're going to go to the same place value here as our critical values. So that t value, which is line number 1 to line 3, approximated to the nearest thousandths, the same as your critical value. We know that test statistic is negative 3.073. The R value, we go over here, is negative 0.782. So R is negative 0.782. I'm writing this stuff down in my iPad, and I'm trying to see here. This is the sample linear correlation coefficient. Now, ladies and gentlemen, that's not really close to -1. So if there is a correlation, we don't know yet. We have to see where the test statistic lies on the decision rule. But we don't know if there's going to be a linear correlation. If there is, it's going to be a weak negative. Because it's negative, sorry, looking for my mute button. It's negative, ladies and gentlemen. We'll see what the decision is. Negative 3.073. So remember, that test statistic, if you have any test statistic that is to the left here of your critical value, and in this case, it's somewhere over here. It's a test statistic value of a negative 0.73. So that test statistic on your decision rule means to reject your null. So you're going to go to the null and you're going to reject the null. Okay, this is in the reject the null region. So, okay, reject your null. By rejecting your null, you are accepting the alternate. And that happens to be the claim, and it happens to be that there is a linear correlation. So your conclusion is, in fact, that there is a linear correlation. And I'll put that here. You do have a linear correlation, but I would say to you that it's a strong negative. Okay? So there is a, linear correlation here. And let's go back up here. All right. And this value here says it's negative, but it's a weak negative because that data doesn't fit in the line very well, but it still satisfies the hypothesis test. Okay, now what's the regression line, right? So they're going to want to know the regression line too. And in your TI, if you go back, it's A plus BX, and you can see that in the calculator. If I go to the TI, it's y equals A plus BX. Where the A value is, we're going to go to the thousandths, 22.257. That's your A value. Your B value is actually a negative value. So it's going to be minus 0.721, and then that's times x. So ladies and gentlemen, this is your regression line. Okay, this is what you're looking for. And you could use this now to predict. So anyway, they want you to go through this, and we've done, one of these kind of questions. This is question number 3, and that's how you go about it. So, I went through a lot of detail here for this, and that's question number 3. We're going to try to do question number 4 now. So you guys can verify that these are the answers you have in your homework. Now, for problem number 4, it says weeks and weight loss. The bivariate sample data below represents the number of weeks a person is on a lose weight quick pills diet. And then you have essentially the cumulative weight loss in pounds. So, you have an X variable, which in theory is independent. You can control that. You have a Y variable. So X here is the number of weeks in your first week, second week, third week, fourth week, fifth week, sixth week, seventh week. And your Y variable is the amount of pounds you lost, and it's cumulative. So week 1, you lost 2 pounds. Week 2, you lost 5. Week 3, you've lost 5 total, right? Week 4, you lost 6. Week 5, you got back to 5 pounds. Week 6, 7. Week 7, 9 pounds. So they want to know if there's a linear correlation between the weeks that you're on the pill and the amount of pounds you lose. And then they're going to say here to use the 5% level of significance to test the claim that there is a linear correlation. Notice we got 5%. Now let's count the data just to see the degree of freedom. 1, 2, 3, 4, 5, 6, 7. So you have the sample size of 7. Your degree of freedom is 7 minus 2. So your degree of freedom is going to be 5 here. Okay? All right, so it's sure enough, that's what this is. Now let's verify that the critical values are going to be, plus or minus 2.571. So if my alpha here is 5% again, as they're saying, you're saying your alpha is 5%, then 2.5 is in each tail. And this is going to be found by using the inverse t function. Inverse t, and the degree of freedom here is 5. So we're going to use the degree of freedom of 5 here. So we're going to find the R value and the T value. Degree of freedom is 5. So let's do that again. Second distribution, inverse T. Left tail, 0.025. And our degree of freedom, I believe, was 5. Let me double check. Sure was. Okay. We're going to paste this. Here we go. And you're going to get negative 2.571 to the nearest thousandths. And sure enough, that's what we got here by using the default. And I went to pink, and I wanted to go to red. And the iPad, this is where we're at. Now, it was 2 tails, so we're going to have the second critical value, positive 2.571. Here's your alpha. Alrighty. So it looks like we're set up here. Remember, your H0, your row is 0. Your H1 row is not 0. Okay, we're going to test this hypothesis. We're going to enter this information in our TI. So let's go ahead and do that. Let's go and enter what we have here. So, okay, TI, we're going to go to Stat, Edit. Notice we have to clear out our list. So I cleared out list 2, scroll up to the title, L1, and hit clear. Now we can enter our data. So the number of weeks data goes in first here. So I got week 1, enter, week 2, enter, week 3, 4, 5, 6, and 7. So this is my independent variable, my dependent variable, the Y variable here. First week, the last 2 pounds. And by the second week, we lost 5. Third week, we're still at the 5-pound loss. Fourth week, 6. 5. We gained some weight. Then we went back down to 7 and ultimately at 9. So we entered the data here, ladies and gentlemen. This is your data. Now, remember what you want to do. We want to create a scatter plot. Hopefully that data will fall in line, right? So I believe you hit second Y. Yes, plot 1 is on. Okay. So I think zoom now, if we scroll all the way down to zoom 9, that should be fine. And sure enough, you have your data. And that data, ladies and gentlemen, looks like you can fit the data in a line, and it looks like the line will have a positive slope. So we are on our way. It looks pretty good. Now you say, what's the rest of this? Well, you hit stat, test. You scroll down to, right? No, we scroll down to linear regression t-test. It's a small sample. Hit enter. The x variable is list 1. The y variable is list 2. Frequency is 1. This is a two-tailed test. We're now ready to calculate. So ladies and gentlemen, let's see what these values are. Let's scroll all the way down. Now, R value. Look at the R value first. Now, the R value, the sample linear correlation coefficient, looks like it's close to 1. I mean, it's not that close to 1, but it's R is 0.897. That's somewhat close to 1. That can still be a weak linear correlation. We have to check the test statistic value. But that's kind of close to 1, right? So remember, we want to, that word close can be debatable. Close to 1. It's close. Now you look at the t value. Let's check to see what we can conclude, right? So t here is approximately, go out to the thousands, positive 4.549. So this here is our test statistic value. We have to see where it lives in the decision rule. 4.549. So that is actually larger than the critical value. So remember, any test statistic that's to the right of 2.579, the critical value, we reject the null. So that critical value is somewhere over here. 4 again point. That's your test statistic. 4.549. So we are to the right of the critical value, that test statistic value. And so what that means is we reject the null. So null, you have been rejected, goodbye. And that implies we accept the alternate, and the alternate happens to be the claim that there is a linear correlation. So yes, that's our conclusion, is that there's a linear correlation. In fact, it's not that close to 1, so this is a linear correlation. I'm going to say this is still a weak correlation. It's weak positive. It's a weak positive linear correlation. It's not as strong where the data really fits on a line. It's kind of weak, and that kind of makes some sense. If you look at this R value, it's not that close to 1. It's kind of close to 1. So you've seen kind of some weak correlation examples here. This was a weak positive, and the prior one was a weak negative. We want to probably put weak negative as well. But, nevertheless, there is a correlation. So let's get the regression line so we could be predictive. So if we go back to the TI, remember y equals a plus bx. Looks like here your regression line is that y will be, a is 2. Yeah. 2 plus 0.893x, because that's the b value. So here's my regression line. I can use this to be predictive. I can predict, the weight loss after a certain number of weeks. So if I said, oh, here's my data, what about week 8? How much pounds? You said, what if, remember, X represents here, the week that you're on these pills. Y represents the number of cumulative pounds you've lost. So just to kind of throw this out there, if I put in, what would it be at 8 weeks? Well, 2 plus 0.893 times 2. And you'll have, well, something's not right. Oh, we didn't use 8. Let's clear that out. 2 plus 0.893 times 8. You would have lost around approximately 9 pounds. This is what I'm saying. And the 8th week, you're going to lose about 9 pounds. That means Y is approximately 9, and it represents the pounds you lost. That's just going back and looking at this. If I said, oh, I wanted to add another, what happens at week 8? Well, it's about 9 pounds, a little bit more. So anyway, ladies and gentlemen, that's kind of how this works. You can be predictive. All right. So let's do another, right? Let's do problem 5 here. And it says, your age and miles run. The bivariate sample data below represents the ages of people in years. Okay, it's your age. I mean, we can't control that, but that's your independent variable. And the number of miles they run per week. Oh, that's interesting. So is there a linear correlation between your age? Like an 18-year-old runs 6 miles. 34-year-old runs more, which is 8. A 50-year-old ran 4. 18, 4. 25, 10 miles. 62, you ran 12 miles. And when you're 20, 20-year-old ran 6 miles. So this is the data, in miles that they ran. Okay, now they're going to say use here the 1% level of significance to test the claim that there is a linear correlation between the two quantities. So notice yes, in the notes 1%. If we count the data values, how many data values are here? 1, 2, 3, 4, 5, 6, 7 again. Sample size is 7. My degree of freedom is 2 less. So the degree of freedom is 5. Okay. All right. Using the 1% level of significance. And sure enough, our degree of freedom is 5 here. Let's test to see if the critical values are, in fact, 4.032. And again, they say 1%. They did say 1%. So the decimal representation here, if alpha is 1%, this is half a percent. Let's be careful here. Alpha is 1%. Half of alpha now. Sorry. Right, half of alpha. This half is going to be 0.5%. So I'm going to move my decimal place 2 spaces. So there's going to be 3 zeros here. So 2 zeros. So sure enough, ladies and gentlemen, I noticed something right off the bat. So yeah, this here, half of alpha is 0.5%, and this is what half of alpha looks numerically. The reason you care about that stuff is because when you find the critical value, you're looking at area to the left when you use the inverse t function. Don't forget, for inverse t, we need the degree of freedom of 5. So area to the left. So we're going to use the calculator now. Second distribution, inverse t, 0.005, the area to the left. It's at the right degree of freedom. We're going to paste that in, and we get a negative 4.032 as a critical value. And sure enough, that is exactly what we said we'd get here. And so this is how you find your critical values, inverse t. Now, since there's 2 critical values, you have to indicate that this is also a critical value on the other side. Positive 4.032. So ladies and gentlemen, it looks like we're pretty good with setting up our formal hypothesis test, right? Your rho is 0 for your null hypothesis. The alternate is rho is not 0. Corresponds to the relationships of having a no linear correlation and a linear correlation. So we got to make sure we we enter our data here and look at the scatter plot and see if this is worth doing. Okay, look at the scatter plot. So let's go to the TI, and we're going to clear that out. We go to Stat, Edit, go up and clear. I cleared the X value. That was from the last problem. Clear the Y value. Now we're ready to enter our data. So an 18-year-old goes in first, and then a 34-year-old. I'll hit enter. I won't scroll down. Then a 50-year-old, and after the 50-year-old is an 18-year-old. And then we have a 25-year-old. We have a 62-year-old. And we end with a 20-year-old. All right. Now let's put the miles that they ran here. Uh-oh, I hit 20. There we go. Now I'm going to put the miles that they ran. Looks like I had to put an enter. There we go. So for the 18-year-old ran 6 miles. 34-year-old ran 8. 50-year-old ran 4 miles. Sounds about right. 18-year-old ran 4 miles. Well, that sounds about right too, maybe. 25-year-old ran 10. 62-year-old ran 12. That could be accurate. 20-year-old ran 6 miles. Okay, here's our data. Remember what we do to graph this. Second, Y. The first plot is on, so good. Now we're ready to hit zoom. Scroll all the way down to zoom stat. And sure enough, ladies and gentlemen, look at that here. I'm going to say to you guys, that doesn't look to me like I can fit that data on a line in any way. Okay, if you really take a look at this, I don't think you can fit that line at all. Doesn't look that good to me at all. So what I would say to you, we don't really have to complete the test in theory. You'd look at this and say, no, there's no way that can be a linear correlation. But okay, try this out. Stat, test, go all the way down. You're going to verify this. You're going to find when you go to linear regression t-test, let's just see. Yeah, everything's good. It's two-tailed test. Okay, we're going to calculate. We're going to verify formally with the hypothesis test, right? So take a look. I'm going to scroll down here. Take a look at the R value, right? R here is 0.459. Okay. 0.459. Now that's actually closer to 0 than it is positive 1. Okay. Because 0.5 is like the halfway point. So that's actually, to me, I think that's closer to 0 than 1. It's not that close, by the way, but it's closer to 0. Our test statistic value, if we try to look for that, let's find it. Okay, is 1.154. That's the t value in your calculator. So we got the R value. We got our test statistic, 1.154. And you say, where does 1.154 live? Well, remember, any test statistic between your critical values, you do not reject the null. And 1.154 is positive, but it's not quite past the 4.032. And in fact, I mean, I'm not even accurate with my sketch that well, because it's probably closer to 0, like 1/4 of the way, okay? But the point I want to make is it's clearly in the do not reject the null region. So if you don't reject the null, okay, you're not rejecting the null. You're accepting the null, but the alternate is out, which is the claim that there is a linear correlation. So here's our conclusion, ladies and gentlemen. The conclusion is that there is no linear correlation. So sure enough, looking at that data, we can't draw a line or fit our data in a line. So here's what this is. There's no linear correlation. That was what the formal hypothesis test has created. So therefore, do not even bother. Do not bother with a regression line because there is no linear correlation. So I want to make sure you're clear with that. Don't even bother with a regression line because it doesn't mean anything. There's no linear correlation. You can't model the data by a line. And that's what they're talking about, ladies and gentlemen. So this is going over the homework, and it was pretty good questions, I would say. I kind of like them. And, you know, check to see if this is what you guys have. Okay? Now I'm going to talk about problem number 6 here. So I think I said it to you guys. I do 3, 4, 5, and 6 for you guys. The rest you have. So this is advertisements in cars, and it says the bivariate sample data below represents the number of advertisements in a month. So this is in theory what you can control. This is your independent variable. Number of advertisements in a month. So when you have 6 advertisements, you know, you sold 15 cars. When you have 20 advertisements, you sold 31 cars. No advertisements, you still sold 10 cars. 14 advertisements, you sold 16. 25 advertisements, you sold 28. 16, you sold 20. 28 and 40, 18 and 25. So, you know, let's see here. I want to make sure you guys understand this is my y variable. So we're going to look at all the x variables and the y variable. We're going to enter that data eventually. And how much data values of bivariate we have? 1, 2, 3, 4, 5, 6, 7, 8. Sample size is 8, which means your degree of freedom is 8 minus 2, which will be 6. There's your degree of freedom. Now, we want to test the claim using the 5% level of significance. The degree of freedom is, in fact, 6. We're going to check our critical value. See if it is 2.447. So remember how we do the process again, ladies and gentlemen. This is a formal process, and I'm going to get rid of this. Don't know why it's there. I might have done this problem already. Did I? I don't know. Anyway, hope not. Oh, might have been left over from some lecture. I think that's what it is. So in one of the classes, I think I might have done it already, but anyway, we'll do it again. Because I think I said do homework 3, 4, 5, and 6. Okay, so what's going on here? Alpha's 5%, 2 tails. Sure enough, okay. 5%, 2 tails. Half of alpha, 2.5%. Area to the left of that value. What's our degree of freedom? It's 6. So remember, we have to enter the degree of freedom. So we go to the calculator. We hit second distribution, inverse t. And that is going to be 0.025 for your, well, the area, yeah, is 0.025 because that's 2.5% with a degree of freedom of 6. And sure enough, we get negative 2.447 here. Okay. And that's the critical value. And don't forget the positive critical value because this is a two-tail test. So this is how we use the TI to find critical values. Okay, we're ready to enter our data formally to get our linear correlation coefficient, sample linear correlation coefficient, the R value, and our test statistic. We're ready to enter this data here in the TI. So, okay. So we go to, again, stat, edit. We're going to clear out these lists. Okay, so scroll to the title, L1 and L2, and hit clear. You're now ready. So 6, enter. 20, enter. 0, enter. 14, enter. 25, enter. 16, enter. 18, enter. And 16, oh, I made a mistake. After 16, there was 28, enter. So let's double check. 25, 16, 28, and then followed by 18. Enter that one. List number 2 now. You got 15. You have 31. You got 10. We have 16. We have 28 and 20. We have 40 followed by 25. Okay, here's our bivariate data entered in the TI, and you say, what do I do with this now? We want to do a scatter plot. So second Y, that's a scatter plot. It's on, so you hit now. I mean, I think you could hit enter even. You could go through everything here again. It is on. But we're going to go to zoom now, all the way to 9, zoom stat. Let's see how this data looks. Now, this is a scatter plot, and it looks like, yes, we can fit some of this data along a line. It looks like it's not the best line, but, a really good line, but it looks like there could be a linear correlation. I think there's going to be a linear correlation. So you might say, okay, what do you do next with this? Well, let's go to stat, test, scroll down to linear regression t-test. Okay, L1 and L2, the X and Y variable are there. Frequency is 1, 2 tails. Okay, sure enough, it's good. Calculate. So let's see what this R value, oh, look at R is about 92. It's 0.92, so 0.920. So I'm going to say this number is close to 1, definitely close to 1. Okay, and the test statistic value, if I go back to the TI, or is negative, oh, it's positive, 5.762. So here's your R value. Here's your test statistic value, 5.762. Let's see where this lives on your decision rule, right? So 5.762, ladies and gentlemen, is past the critical value of 2.447. We're going to reject the null because our test statistic is like way out here, Test statistic 5.762. It is in the reject the null region. So you say, I reject the null? Yes. If you reject the null, and you guys remember that, get rid of the null, you're accepting the alternate, which happens to be your claim that there is a linear correlation, and that's your conclusion. So you can say, it's a linear correlation. So just a question I have for you is, that R value is close to 1. It's not very close to 1. It's not like it's 99 or 95 or even, 97. It's about 92. I'm going to go out and say, if I looked at remember that, there's kind of a strong correlation maybe. It's a positive correlation, so a strong positive slope. R value is positive. Strong positive correlation. Therefore, we can use and we can get our regression line. It's going to be used to predict. We can be predictive, so we need the A and B values. So going back to the TI, maybe I'll scroll in if I can. You can see some things that maybe you can see the A and B value better. I just like to move that around. Can't seem to move it around very well. Well, A is 7.716 plus the B value is 0.971. And then you put your X variable. Okay. So this is gold. This is what you're looking for. This is your regression line. And, you can actually determine now, how many advertisements. If we want to have 30 advertisements, right? And say put a 30 down here. If we want 30 advertisements, then how many cars are we going to sell after 30 advertisements? So just to kind of be a bit predictive and say, well, when X here, this number here is, and I guess the yellow or the orange, when that number is 30, let's see what Y becomes. Just to kind of give you a predictive aspect of this here. So clear that out. 7.716 plus 0.971 times that 30 number of advertisements. if we approximate the whole number, we can expect to sell 37 cars. Is that right? So this is going to be 37 cars, right? I believe. Yeah. Advertisements to cars sold. We can expect to have that 37. So we need 30 advertisements to sell 37 cars, I guess. We're predictive. Anyway, ladies and gentlemen, I believe the next or the last one is the pizza one, and I've done that one in class. So you do now have, ladies and gentlemen, looks to me, I'll let you guys do the CSI one, have some fun. Well, should we do CSI? I'm going to get somebody email me saying, Mr. Judge, you didn't do the CSI. I need it. I won't live without the CSI problem. How do I know if I got it right or wrong? We'll try this one out. So what do they say? Guess we'll do CSI. The bivariate sample data represents the shoe print at the crime scene and the height of the convicted male who committed the crime at the scene. Yikes. So shoe print. This is my X variable. All of these are my X variables, the shoe print. So there's an X variable. And then the height. So is there a relationship between the height and the shoe print? Maybe. This is a nice CSI question. I like it. Okay. So what are they saying here? Data represents the shoe print and the height of the convicted male. Use the 5% level of significance. It says to claim there's a linear correlation. So sure enough, they have 5%. Let's count our data. We have 1, 2, 3, 4, 5 data values. So if my data value is 5, degree of freedom is 2 less. 5 minus 2 is 3. So sure enough, that's accurate. Let's see if the critical values are plus or minus 3.182. All right, 5% degree of freedom is 3. So yes, remember this. 5% is alpha. 2.5% is in the left tail. We're going to find the critical value. So remember, second distribution, it's inverse t to do that. Still 0.025, but now my degree of freedom is 3 here. So we're going to paste that in. And ladies and gentlemen, negative 3.182. And sure enough, negative 3.182. And the other one is positive. There's 2 critical values. Positive 3.182. You need both of them. So far, so good. We set up our hypothesis test correctly. Rho here is 0 for the null. Rho is not 0 for the alternate. That's going to be our claim. And ladies and gentlemen, we're good to take a look at what this looks like on the scatter plot. We're good to proceed. So let's punch this in. Now be careful. They gave you data in a row, not even in a column. So, okay, no big deal. We're going to go to I believe it's stat, edit, scroll up and clear out that row. Move to the left, scroll up, clear out that row. Now enter your data here. So the first row, 29.7, and then another 29.7. All right. 31.4, and then a 31.8. And after that is a 27.6. So this is the shoe print in centimeters. Now let's go to the height of the individual. 175.3, we'll enter that. 177.8, enter that. 185.4, enter that. 175.3, we enter that one. And then 1 72.7. So ladies and gentlemen, we got our bivariate data. Second Y. Well, that's the one we're looking for. It is on. All right. Okay, I guess now we have to hit zoom and then zoom stat. And, I don't know. That doesn't look like it fits in the line at all. All my data, 1, 2, 3, 4, 5 did values. Maybe. We'll see. We're going to have to check to see the R and T values here. All right, let's see what we have. Go to stat. Go to test. Go all the way down to linear T, right? Linear regression t-test, small sample. Everything looks good to me. L1 and L2, frequency is 1, two-tail test. We're going to calculate. Looks good. So let's see what that R value is. Oh, R is 0.591. Wow. Yeah, I don't know. 0.591. If there is a linear correlation, it's going to be weak. It's not even close to 1. It's like closer to 5.5. Well, no. Let's see what the test statistic tells us. We got to look at that test statistic. The test statistic will tell us. So T is positive 1.269. If we go to the nearest thousandths, then this is 1.270. All right, 1.270. I guess that's our test statistic. Okay, where does that live in our decision rule? Well, remember, any test statistic between negative 3.182, positive 3.182 do not reject the null. Now, this test statistic that we just got is 1.270, so it's positive, and 1.2, it's like somewhere over here, 1.270. Okay, it's not even like halfway, I think. So there's where your test statistic will live in your decision rule. Do not reject the null. So what does it mean not to reject the null, ladies and gentlemen? What that means, if you don't reject the null, you're accepting the null. Do not reject it. It means accept it. The alternate is gone, though. And that's your claim. So, ladies and gentlemen, there is no linear correlation here. So if there is no linear correlation, here's your conclusion. There is no linear correlation. And that kind of makes sense because that's a nowhere near positive 1 or really even negative 1. There's no linear correlation. That's what our hypothesis test concludes. And what that means, there is no need for a regression line to predict. No need, ladies and gentlemen, because there's no linear correlation. That means you can't model the data with a line. And even going back to the calculator, if I go to the, seconds, distribution, blah, 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 enter, zoom 9, zoom stat, that's going to give us our scatter plot. That data does not look like it can fit in a line. I hate to say it. Okay, it's no linear correlation at all. So anyway, I hope you guys enjoyed this. I'm going to send you the announcement in Canvas. I hope you guys enjoy the video. You guys take care. Stay safe. Have a wonderful evening.